I recommend that before we begin, you read the introduction to the demo videos series. In this video, I will demonstrate high-level and register transfer level design with our tool Syntagate, a product of Synthesa company. This tool implements the design of control and data path intensive systems with very complex control units containing numerous inputs and outputs. Syntagate performs automatic synthesis of digital system from behavioral specification to the high level and the register transfer level. The main difference between Syntagate and our design tools is that the designer doesn't need to use hardware description languages. Instead, Syntagate uses algorithmic state machines at the different steps of design. As an example, we will discuss the design of lossless codec with Altera's memory in real time. In this codec, uncompressed data is written into memory M1. The encoder reads this data from M1, compresses it, and writes this compressed data into memory M2. When the decoder reads data from memory M2, decompresses it, and writes the compressed data into memory M3. If you are not interested in codec itself, don't spend time trying to understand how codec works. It is more important to understand how Syntagate works, how it, beginning from ISMs, no VHDL or Verilog files, in several seconds designs rather complex digital systems at the high level and register transfer level. It is the working folder for our design. At the beginning of our design we have three folders: Initial, Components and Spec. Let's begin from folder Initial. Folder Initial contains two modes, main coder and main decoder. In Syntagate there are no constraints on the number of modes. The design can contain tens or even hundreds modes. Let's open main coder. Now you see one of two modes, main coder, constructed with our GUI ISM creator. You can find more information about ISM creator at synthesa.com, and you can even download it and try it for free. As you see, ISM contains vertex begin, vertex end, and operator in conditional vertices. The Boolean expression can be written in conditional vertex. An operator with one, two, or more micro-operations can be written in the operator vertex. There are two kinds of micro-operations in ASM. The first kind is a simple micro-operation containing assignment :equal. For example, here and here. The second kind of micro-operation is a component micro-operation. We call it sub-ASM or a generalized operator. This kind of micro-operation doesn't contain an assigned operator : equal. In this example, they are indicated by the color yellow, but the color is not important. These operators are sub-ASMs and will be included in the mother's ASM to get the whole behavior of digital system. Sub-ASMs can contain sub-ASMs as well, and there are no constraints on the number of sub-ASMs and the number of levels of this inclusion. Coder contains two sub-ASMs, DMA cycle and PEG data. To open sub-ASM from the mother ASM, I must right-click the corresponding generalized operator or sub-ASM and select Open. And we have sub-ASM. And we can continue. Open, open, and so on. Open, open. Using such generalized operators allow us to implement top-to-bottom design. And the designer doesn't need to design complex ISMs. As a rule, they contain about 7 to 10 vertices. The designer must put the generalized operators in folder General, which is a subfolder of folder Initial. When I click Build in ISM Creator, Syntagate immediately compiles this schematic into two files in folder Initial, main coder GSA. This file presents ISM as two connected lists. And file maincoder.txt, a text file with the contents of vertices in the ISM. These files, JSA and TXT, are internal representation of ISM, and Syntagate works with them, not with its picture. From file maincoder.txt we see that it contains 4 operators, y1, var4, 6 microoperations, y1, y6, and 2 logical conditions, x1, x2. And I must build for our second mode main decoder. Build, and I get the similar files maincoder.jsa and maincoder.txt. Let's return to our folders. If the designer would like to use a pre-designed IP core, they should put it in folder components. In this design, we use memory core from Altera company. I had generated this file memory Altera from the tool Quartus of Altera. To implement high-level synthesis of digital system, the designer doesn't have to define each port and signal. Syntagate program automatically creates an XML code of a functional specification. It's an folder spec. This file or this specification contains 13 ports, 23 signals and 3 variables. The designer only needs to insert the length of several ports and signals into this specification in the dialog mode. Again, not all, but only a very small part of them. Thus, before the design, we have ASD, GSA, and TXT files in folder initial and its subfolder general, file funcmi spec in folder spec, and file memory Altera in folder components. Other files in folder spec and components will be constructed automatically in the process of a design. Now we can begin the design of our codec. It is our simple interface to demonstrate the design tool Syntagate. If the designer begins from ISMs, from GUI ISM Creator, we must check the box ISM in section Source. If from System C, check the box System C. If from VHDL, check the box VHDL. This figure demonstrates that ISM can be presented as a graph drawn in GUI ISM Creator, as a text in pseudocode of System C, or a text in pseudocode of VHDL. In this figure on the left you see the ISM of main coder, one of two modes of a codec constructed with ISM Creator. The designer doesn't present the design in System C or VHDL. The center and right images in this figure contain ISM presented as a text. They don't have definition of ports, signals, or variables. If you compare this text with the left image, you will understand that they present the same behavior. When I am talking about ISMs in System C or in VHDL, these ISMs are only graphs presented with operators of System C or VHDL. We made options for the case if a designer would like to draw ISMs, but prefer to write them in the text file. Nevertheless, I am highly advised to draw ISMs in ISM Creator. Let's begin our design of codec with Altera's memory. I must insert the name of working folder, codec Altera GUI, in the project folder of our interface. I check the box ISM as I begin from ISMs from GUI. Check the box Combine ISM. I have two modes in this design, main coder and main decoder. And I check box include generalized because I have several sub-ASMs in folder general. To design codec at the high level and RTL, I must click run. In about 4 seconds, the design is complete. The time of design is written in file HLS total time. As a result, we have 13 new folders in the working folder. Each folder contains one or several stages of design together with complete documentation of this stage. The result of high-level synthesis is presented in folder HLS. Syntagate automatically constructs two designs at the same time. The first in VHDL, file funcmyVHD, and the second in systemc, funcmyCpp. File funcmyVHD contains 85 states and 795 lines. This FSM presents our whole design at the high level in VHDL. File funcmyCpp contains the same 85 states and it's a little bit longer, 1087 lines. After preparing a test bench, the designer can simulate the functional project with any simulation tool. The designer must choose what we would like to use in the simulation at the high level, version in VHDL or version in systemc. The same test bench can be used at the last stage of design, at the RTL level. I will return to this simulation a bit later. Now let's look at the RTL design. In folder RTL, Syntagate generates VHDL codes for 23 components of data path listed in file components VHD. At the last step of data path design, Syntagate automatically instantiates these components in data path in this folder, dpvhd. At the bottom of this file, you will see that it contains 420 lines and 50 instantiated components. The number of instantiated components is more than the number of VHDL files in folder RTL because some components are used several times. Syntagate automatically designed the control unit, file structem VHD. The control unit is a finite state machine with 92 states and 992 lines. At the last stage, Syntagate creates the top level, file top VHD, combining two components, the control unit and data path. The entity of this file contains inputs and outputs of the design systems. Its architecture has two components. Struct M, its control unit, and DP, data path. With signals connecting with two components. Here the signals. The instantiation of these two components are U1 FSM and U2 DP. Now let's design our codec from ISMs presented in systemc. At the beginning of design we have three folders, initial, spec and components. Folder initial contains two files, main coder CPP and main decoder CPP. It's main coder. CPP files of sub-ASMs are in folder general of a folder initial. To make the design, I must change the name of working folder and I must change ASM by systemc in section source. And I must click run. And in about 4 seconds the design is complete. As a result, we have 13 new folders in working folder. The next step is to present the design of our codec from ASM and VHDL. It is our working folder, and to make design once again I must use name of working folder and put it here in our interface. And I must change systemc by VHDL. And when I click run, I get 13 new folders in a working folder. You can find the main folders of these three designs on our site synthese.com. If you compare the last two designs, you will find that they consigned at the high level and RTL. It is evident because the same program compiles our ASMs in systemc and VHDL files into the same JSA and TXT files from which Syntagate begins the design. Now let's talk about simulation of codec. We can use any design from these three, beginning from GUI, from CPP or from VHD. Of course, for any of them, we can use the same test bench. Let's do that for our last design, codec VHD. To begin with simulation, I prepared the folder simulation and I will move it in our folder. This folder contains two subfolders, HLS for simulation at the high level and RTL for simulation at the register transfer level. In both this folder, I put the same TXT file, flag Canada, the text file presenting an image of a Canadian flag. To understand the test bench, let's return to the structure of our codec with three memories. In our codec, uncompressed data is written into memory M1. The encoder reads this data from M1, compresses it, and writes the compressed data into memory M2. When the decoder reads data from memory M2, decompresses it, and writes decompressed data into memory M3. Thus, the main idea in the test bench is to compare the file at the output of M3 with the file at the input of M1. Really, test benches at HLS and RTL are equal. I gave them different names, FuncMITB for simulation at the high level and TopTB for simulation at the register transfer level. Let's compare them. The difference is only in the names of entities, architecture, and components. No, I almost forgot. High-level synthesis uses the package myPackage and RTL uses the package components. To make the simulation, I must copy the result of high-level synthesis from folder HLS into folder simulation HLS for simulation at the high level. So I go to folder HLS take FunkMI VHD in my package, copy simulation, HLS, paste. And I must make the same with result of the RTL. I must copy all files from this, copy, go to simulation in folder RTL, paste. I won't take your time by showing you this simulation. You can do that yourself with any simulation tools. To make sure that the design is correct, compare files flag Canada at the input of M1 and the compressed file at the output of M3. At the high level, I used two files, FunkMI VHD and my package VHD for simulation, but at the RTL, this would require 27 files. This is the reason that the simulation at RTL is several times longer than the simulation at the high level. On my personal computer, HLS simulation is a little bit less than 2 seconds, which is 6 times faster than at the RTL. Once again, we have implemented 3 whole designs, each containing more than 300 files in about 4 seconds each. At the beginning, we only had algorithmic state machines and nothing else, no VHDL, no Verilogs. You can find more about design methodology realized in Syntagate in my books, Finite State Machines and Algorithmic State Machines, and the second one, High-Level Synthesis of Digital Systems. These books are available on Amazon in ebook and paperback. I would like to underline that Syntagate allows quickly implement, check, and estimate multiple design versions, find and optimize solutions for design problems, produce design documentation automatically, and simplify the digital system verification problems. Syntagate covers most digital system design from DSP to processing units. It can be used in the design of robots, controllers, processors, IoT and AI systems, digital systems for automated and autonomous cars, etc. Likewise, Syntagate can be effectively used in numerous university courses. You can get additional information from our website synthese.com. Thank you.